All right. Hey guys, my name is Imran, and today we'll be going over our intrusion detection system project. As for the table of contents for today, we will be covering what is a intrusion detection system, the data set that we used, how we pre-processed the data, then our feature selection methods, then the training model, and the various different machine learning algorithms that we will be using. And at the end, we will finally be comparing our results with the algorithms that we used. So to start off with, as an introduction as to what an intrusion detection system is, it's basically a security technology designed to monitor network or system activities for malicious actions or policy violations. It continuously monitors traffic or system operations to detect unusual behavior or activities. It analyzes patterns that may indicate a potential threat, such as unauthorized access or the exploitation of vulnerabilities. Machine learning based intrusion system is becoming more popular these days because they have the ability to learn from larger data sets and adapt and identify future threats. So in this project, we selected the KDD Cup 99 data set. It's a very well-known resource in the field of security, which is often used for benchmarking intrusion detection system. So for this data set, it provides us like a very rich set of data specifically designed for evaluating the performance of the IDS. Includes a variety of different type of attacks with normal connections to test how well a system can identify abnormal activities. And from the data set, we counted a total of 42 features or 42 columns. It also has a range of simulated network interactions that represent different types of network-based attacks, such as backdoors, buffer overflows, and DDoS. This helps developing and testing systems that can be used to detect and differentiate various threats. And it was also developed for the third International Knowledge Discovery and Data Mining Tools Competition. Dataset has been, in general, been a fantastic source for an IDS system. So from the data set, we counted 42 distinct features or columns. It had various different mixed of network features. So there were certain basic ones, such as like the source and destination IP addresses. It also contained some advanced features, such as how long the user was connected or the number of failed attempts for a login, etc. So on the right side, we have like a snippet of the image that we have when we ran the data set. You can see there's 42 in total. It shows 41 because the index starts from 0, but it also shows you the number of columns and the amount of data and the data type and all that stuff. Next, we will be going over the import. So the first thing we do is we import a library called sklearn. One of the dependencies that we use was the random forest classifier. This is an import for the random forest classifier class, which is a machine learning algorithm for classification that operates by constructing a multitude of decision trees at a training time. Then we have accuracy score, recall score, precision score, F1, confusion matrix. These are all performance matrix that we use to evaluate the quality of the prediction that were made by the classification algorithms that we use. We also use cross-val score, which is used to perform cross validations, which is a technique for assessing how the result of the statistical analysis will be generalized to an independent data set. Then we also use train test split. This is used to split the data set into training set and the data set, which is pretty important because for evaluating the performance of the machine learning model that we're going to be using. Next, we use some common Python data manipulation libraries. So we use pandas and numpys. Pandas is used for data manipulation and analysis. We also use NumPy, which is another Python library, which basically used for multidimensional arrays, matrices. So used to store some data structures. Then we also use Seaborn and Matplot. This is for data visualization. It's part of the Python library. You can basically provide numerical information and it displays it in like a much better UI. and Seaborn is based on the Matplotlib, so it's like a high-level interface for drawing like cool graphs and stuff like that. Then another miscellaneous import that we had was the time module from the Python library. Is usually just for performance metrics and other small stuff. So next we move on to the pre-processing part. So we first downloaded the data set in a CSV file from Kaggle and uploaded it into our Jupyter notebook. We then printed out the list of columns and the data frame information to test if we are able to load the data. So on the image on the right, you'll see that it shows the column and then the data frame information about the same. Next, we move on to part two of the pre-processing. So before we proceed with training the data model, we want to make sure that our data is as clean as possible or as clean as we can get. This helps to increase accuracy of the machine learning model. So for starters, we removed all entries having the missing values. So we are basically doing a null check in our code. Then after that, we do remove all duplicate rows. And then we go to counting the number of occurrences of each label. Then we convert the certain categorical data into numerical data using the one-hot encoding since we're trying to classify. Then we work on the normalization of the data where we normalize different labels and attack label. And then we basically process the data frame into a new CSV file. And then on the image on the right, it shows you the snippet of the file once this part is run in Jupyter Notebook. Then for the pre-processing, this is the third step. We further clean our data set by using or basically dropping some of the columns that were not really relevant to our machine learning model. So we basically drop the column, and after that, we display the data frame. So on the image on the right, it was a pretty big list, but I basically just show you like a snippet of how the result would look like after we drop those columns as well. Um, Next, we move on to feature selection. So feature selection is pretty important process in machine learning because it involves selecting the most useful features from the data set. The main goal of this is to improve the model's performance by removing irrelevant and redundant or so-called nosy data. This basically makes the model more efficient and also makes it a bit more accurate. So by choosing the most important features, feature selection reduces the complexity of the model. This makes the model faster to train and can help with avoiding overfitting, where the model is too closely fitted to the training data and performs poorly on the new data. So for our feature selection, we have used the PCA, which stands for Principal Component Analysis. It is a unsupervised machine learning feature selection. It's pretty commonly used in the machine learning or machine learning world. A set of correlated variables is converted into a new set of uncorrelated variables known as the principal component using the statistical approach of PCA, and the amount of variation in the data is captured by the first principal component, followed by the second, and then so on and so forth. So by choosing the top principal component that account for the majority of the variation in the data, PCA can be used as a feature selection strategy as the input space dimensionally can be decreased while keeping the data's integrity. This leads to shorter training times and improved generalization capabilities. After that, we basically use the random forest feature to train the model set using the dot fit method. So in our code, the X is basically represents the input features and the Y represents the target variable or like the output you're trying to predict. The fitting process involves the random forest learning, which features the best split to basically split the data to classify the Y correctly. So after making the classification decision, um, the features with like the higher scores are considered like more important and vice versa. So this information is pretty important because when you want to reduce the number of input features to a smaller size, this can actually give like weightage or importance of each feature that we're working on. So on the right side, you can see like a snippet of the feature name, and then followed by the importance of the same.
Hey, I am Irfan, and I'll be taking over the second half of this presentation. So next we did the training. We split the data into training set and testing set, and then the training set was used to fit the model, and it was used to evaluate its performance on the data. And for the ratio, we used 60% as training set and 40% as the testing set. Next slide, please. And then after that, we started with the second part of our training. So at the very top, we just imported the train test split function from the model selection module of the sklearn library. This is mainly used to divide the data set into training and testing sets. And then after that, we split the data set. We are using the train test split to divide our function into two parts, the X train and Y train. Those are the features and labels for training the model, and X test and Y test are the features and labels for testing the model. And then on that second line in that same block, we specify that 40% of the data should be reserved for testing, which it says over there like 0.4. And then we're setting the random state to 42. And then the random state ensures that our splits are reproducible. So anyone using the same random state will get the exact same split. And then after that, we are displaying the shapes of the data set. So we just create a tuple called shapes, and that holds the dimensions for our training and testing sets. And then we just print them out. And then after that, we are also saving the data sets to the CSV files. And then finally, we just create a dictionary mapping the file names to the corresponding data frames. And then we also loop through this dictionary, saving each data frame to a CSV file without an index. And that's why we have the index is equal to false over there. And then for the output for this block of code is going to be the CSV files that are saved. And on the right, we can see the output. And I will go over um, the comparison with all of our models at the end. Next slide, please. Okay, so over here, we start off with the decision tree classifier. So at the top, we are importing the decision tree model, and then we're using, as already discussed, we are using the accuracy score, recall score, precision score, F1 score, and confusion matrix to evaluate the performance of the model. And then we're also using cross-val score for running the cross validation, and then the time module to track the time. And then for the first line, decision tree is equal to decision tree classifier. We're just creating an instance of the decision tree classifier. And then on the following lines, we are training the model. So here we measure what time it takes to train the decision tree on the training data. And the duration is printed in seconds. And then after that, we are making predictions on the X test, and then we also print it out. After that, we are doing the cross validation. We evaluate our decision tree using 10 folds, 10-fold cross validation on the training set, and then we just print the output. Then after that, we just print out all the performance matrix, I mean the performance metrics of the model, which is the F1 recall, precision, F1 score, and confusion matrix. Next slide, please. So after that, we go over the random forest classifier. Um, at the very top, we're using sklearn ensemble, which uses the random forest algorithm. And then we use the sklearn metrics to evaluate the model. And then cross-val score and time, like I previously mentioned, is just for cross-validation purposes and just to track the time. And then for the first line of the actual logic, we are initializing the random forest model, and we are specifying that we need 100 trees, where it says n estimators is equal to 100. And then we train the random forest, and then we're using the time module just to track that, and then we output the um, the training time. Then after that, we also predict the random forest that we make on the X test, and then we print out the time. Then we use cross validation, print out the accuracy of it, and then likewise, we're just um, outputting all of the performance metrics. And to your right, you can also see what those metrics are. And then also, I would like to highlight that this is very uh, it has a very good cross validation score as well as accuracy. And I will talk more about this in the conclusion where I just compare all of the um, metrics, performance metrics. Next slide, please. So next I'll go over the Gaussian naive Bayes classifier. So in the imports, we have the Gaussian NB to use that algorithm, and then metrics, as I stated before, same with val score and time. I'll just go over this quickly, and then we initialize the Gaussian NB for the first line of the logic. And then after that, same way, we're just training the data and outputting the result. Same way, we are predicting based on what is inside the X test and outputting that. And we are doing cross validation on it as well, which is again outputted. And again, we are just um, outputting all of the performance metrics at the end. And then the output shows that um, it has quick training and prediction times. And it also shows that the cross-validation scores and mean accuracy um, may not perform consistently across different data subsets. And also the performance metrics reveal that um, the recall is extremely high, as well as the precision and overall accuracy. Oh, I'm sorry. The recall is extremely high, but the precision and overall accuracy are lower. So this means that there might be a lot of false positives. And then we can also look at the confusion matrix, and we can see that there's a lot of false positive comparison to the uh, true negatives. Next slide, please. So for the final one, we are using XG boost classifier, um, So in the imports, we use the XGBoost library to use that. And then same as with the other models, we're using metrics, val score, time, training the classifier, making predictions on it, cross-validating it, just like in the other models. I won't go over this because we already covered it in the previous models. And then finally, we're also calculating the performance metrics. And then on the right-hand side, we can see the output. So the training and prediction times for the XGBoost classifier are shown. The cross-validation results are very high. So this would suggest that the model has excellent performance. The accuracy, recall, precision, and F1 scores are also very good. And the confusion matrix doesn't really look way too off. So it's a very good model. Next slide, please. So this is where we compare all the results. So just to like the way we are showing this is we just added all the metrics inside of a list, and we are outputting the F1 score, precision, recall, and accuracy, respectively. So for the output on the right-hand side, the decision tree has perfect recall, but lower precision and accuracy. The random forest and XGBoost have near perfect scores on all metrics, which indicates that this is the probably one of the best models on this data set. And then the Gaussian naive Bayes has high recall, but very low precision and accuracy. So this may suggest that it has more false positives compared to other models. So as like an analysis standpoint, the random forest and XGBoost have the perfect classification on this data set, and the decision tree has lower performance metrics, uh, which is to be expected because it's a simple model. And then the Gaussian naive Bayes has a high recall, shows lower precision and accuracy, which might mean that it has higher false positive. And then ensemble methods like random forest and XGBoost tend to outperform single models like decision trees and are simpler classifiers like Gaussian naive Bayes on many other tasks. And yeah, that will be all for our presentation. Thank you.